We use Hooke's law to introduce quantification of elastic potential energy. What does that mean? Well, we can determine how much elastic potential energy is stored or released by looking at the amount of stretch or compression of an object, or by looking more specifically at the change in the object's length. The equation that we're going to use from our graph is the force involved in stretching or compressing, in this case stretching our spring, is equal to negative K times delta X. The negative sign means that the force is applied in one direction and the change in length is in another direction. What this force is actually showing is this is the force that is needed by the spring to apply to return the object to its particular direction. Because if you think about the lab that you did, you applied the force down by adding mass to your spring, and the length increased down. So the force and the delta X were in the same direction. What this force is actually giving us is the force the spring has to apply to restore its original position. What we're looking at here is energy pi is showing us the amount of energy stored in the spring relative to the length change of the spring. And we have a graph here similar to the one that you generate for the lab, and so the spring stretch and the amount of energy stored are corresponding for our energy pi diagrams here, our spring diagram for stretching here, and our graph along the force delta X line here. We learned earlier that work is equal to force parallel times distance. Okay, so if I multiply force times distance, I'll get work. If I take a look at this graph, I have a triangle here. If I wanted to find the area of the triangle, I'd take the force and I'd take this and I'd multiply them, and then I'd multiply by 1/2. That's really similar to this work equation. So what that indicates, and what we will eventually find, is that the area under the curve on a force delta X graph is the energy stored by a spring. So if we put that into a mathematical relationship, we get elastic potential energy equals 1/2 times the force times the change in X. That's the area of a triangle. We're going to assume that our line starts at 0 so that we have areas of triangles representing our energy being stored. Well, that's all well and good, but what if I want to find energy stored when I go from position 1 to position 2? Well, I can simply find the area of triangle 1, which is this, and I can find the area of triangle 2, which is this, and take the difference. What I'm left with then is the area of interest, which is right here. There's got to be an easier way. Well, there is, fortunately for us. We found that force equals negative K delta X. So if I take this and I substitute in for force in each case, I'll get something a little bit different. So I get elastic potential energy equals 1/2 negative K delta X2 times delta X2 minus 1/2 K delta X1 times delta X1. Now I reorganize and I cluster and I rearrange, and what I get is E equals 1/2 K, pull it out, delta X2 squared minus delta X. And that simplifies to elastic potential energy equals 1/2 times K times the change in X squared. And this equation is a whole lot easier than the one above, and so this is our equation for elastic potential energy. We saw it way back at the beginning when we got the equation for elastic potential energy. Here's how we get it. Now in some cases, for your Hooke's law lab, your y-intercept was not equal to 0. When that happens, we have something going on called a compression force, and that is the initial amount of force that the spring exerts on itself. And in order to get a spring to stretch, you have to supply at least the compression force quantity before you can get it to stretch. Very stiff springs tend to have compression forces. Flexible, lightweight, loose springs generally don't have compression forces, but they are relatively easy to identify graphically, And when we're dealing with calculations, you need to keep that in mind. When we're dealing with calculations, you need to keep that in mind. Most of the time when we do problems, we will assume the spring has no compression force, just because that makes life easier. All right, let's take a look at some examples here. I have a spring constant, that's the K value, of 50 newtons per meter. So I'm supposed to write the Hooke's law equation for this spring. All right, Hooke's law is just the relationship between force, spring constant, and change in position. So force equals negative 50 newtons per meter times delta x. There we go. Now I'm supposed to graph it. Well, if I make each of these tick marks here 0.1, so this is going to be 0.5, here's 0.3, here's 0.1. Okay, so if I take 0.5 times 50, I get 25 up here. So here's 15, and here's 5. So now to graph it, I need a line. So I'm going to start at 0, and I'm going to come up there. And so there is my line representing from 0 to 0.5 meters, force versus change in x. Okay, now I'm supposed to determine the area under the line. Well, it's a triangle. So there's my triangle. There's the area under. What does this represent? Well, we said before that the area under the curve on a force versus delta x line is the energy stored by the spring. And the area is the area of a triangle, so we have 1/2 the base times the height. So we have 1/2. The base is delta x, so that's 0.5 meters. The height is force, so that is 25 newtons. And so I get 6.25 joules of energy stored by this spring. Determine the formula for the area. Well, we did it. It's right here. Find the work to stretch the spring from 0.3 to 0.5. So the area that I want is shown there. It's the area between 0.3 and 0.5. It's a rectangle plus a triangle or a trapezoid. So what I need to do is geometrically or algebraically find that area. I can find the area of the rectangle plus the area of the triangle, or I can find the area of a trapezoid. So let's do the area of the trapezoid. So trapezoid is height 1 plus height 2 times 1/2 times the base. So I have 1/2. Height 1 is 15 newtons. Height 2 is 25 newtons. My change in base is 0.2 meters. So I do the algebra and I end up with 4 joules. So going from 0.3 to 0.5 meters for stretch, I generate 4 joules of energy. That's a lot compared to the total amount of energy, which is 6.25. That means it didn't take a whole lot of energy to stretch the initial distance. And that's something that we're going to find with springs. It's because I have that square determined there for energy, the change in length drastically increases the amount of energy that I store.